Hey, you all! Tonight, we're falling asleep while learning why parallel lines can both meet and not meet. Sounds impossible, doesn't it? After all, in school, we were taught, firmly, confidently, that parallel lines never cross. They run side by side forever, like railroad tracks stretching into the horizon, always equidistant, never converging. That's Euclid's fifth postulate, the parallel postulate, and for over 2,000 years, it seemed like an unshakable truth about space and geometry. But here's the twist: in our actual universe, parallel lines can meet. Not in some abstract thought experiment, but in real, measurable, physical reality. And they can also not meet. Both statements are true, depending on how you look at space itself. That's not a paradox. It's physics. It's geometry. It's Einstein. And yes, it even keeps your GPS working while you drive to the grocery store at midnight. And if this sparks your curiosity, subscribe for more mind-bending topics delivered straight to your dreams. So settle in. Breathe slowly. Let your thoughts soften. We're not just going to tell you this, we're going to walk you through it, step by step, idea by idea, gently, like tracing the curve of the Earth with your fingertip. We'll begin on the surface of a sphere, something familiar, our planet. Then we'll lift off into space, into the warped geometry of gravity, into the very fabric of space-time. We'll meet great minds, Gauss, Riemann, Einstein, and see how their insights changed everything. We'll talk about how satellites orbit, how time slows down near massive objects, how your phone knows where you are because parallel lines behave strangely in curved space. And all of it, every single piece, starts with a simple question: what if the rules of geometry aren't universal? What if they depend on the shape of the world you're standing on? Let's begin with the humble orange. Imagine holding an orange in your hands. Smooth, round, slightly dimpled skin. Now take a marker, any color, and draw a straight line from the top to the bottom. Not curving left or right, just as straight as you can make it across the surface. That's a great circle, the largest possible circle you can draw on a sphere, like the equator or a line of longitude. In fact, all lines of longitude are great circles. They run from the North Pole to the South Pole. Now draw another one, say, 15 degrees to the east. Another straight line, same rules. Keep going. Every 15 degrees, 0, 15, 30, 45, all the way around. You now have 12 lines, all straight from the orange's surface, all passing through both poles. Here's the key: at the equator, these lines are perfectly parallel. Look at any two adjacent lines of longitude, they are separated by the same distance all along the equator. If you placed tiny cars on those lines and drove them eastward along the equator, they'd stay the same distance apart, never gaining or losing ground on each other. By the definition we use on flat maps, they are parallel. But now, follow them north. As you move toward the North Pole, something remarkable happens. The distance between the lines shrinks. The cars driving north on those longitude lines begin to drift toward each other, not because they're turning, but because the space itself, the surface of the orange, is curving. And at the North Pole? They meet. All of them. Every single line of longitude converges at that single point. So here's our first shock: on the surface of a sphere, lines that are parallel at one location can and do intersect at another. They are straight, in the sense that they're the shortest paths between points on the surface, called geodesics, and yet they cross. That means Euclid's parallel postulate, that through a point not on a given line, there is exactly one line parallel to the given line, fails completely on a sphere. In fact, on a sphere, there are 0 parallel lines through a point not on a given great circle. Every great circle intersects every other great circle, at 2 points, to be precise. Now, you might say, well, that's just the surface. The orange is curved in 3D space, but the lines themselves are bending because the surface is embedded in a higher dimension. And you'd be partially right. But here's the deeper insight: the creatures living on the surface, tiny two-dimensional beings, like ants crawling on the orange, would never need to know about the third dimension to detect this curvature. They could figure it out from within their world, using only measurements they make on the surface. How? Through triangles. In flat, Euclidean geometry, the kind on a tabletop, the sum of the interior angles of any triangle is always 180 degrees. Always. Draw a triangle with a ruler and protractor, 3 straight sides, 3 corners, add them up, 180. It never changes. That's a theorem, proven from Euclid's axioms. But now, draw a triangle on the orange. Start at the North Pole. Go straight down to the equator along the prime meridian, 0 degrees longitude. Then, at the equator, turn 90 degrees and walk east along the equator for 90 degrees of longitude, say, to 90 degrees east. Then, from there, walk straight back to the North Pole, again, following a great circle. You've just drawn a triangle. Let's examine its angles. At the North Pole, the angle between the 2 longitude lines is 90 degrees, the same as the longitude difference you walked along the equator. At the first equator point, 0 degrees, 0 latitude, the angle between the meridian and the equator is also 90 degrees, you turn sharply east. Same at the second point, 90 degrees east, 0 latitude, another right angle. So this triangle has 3 angles, 90, 90, and 90. Sum, 270 degrees. 270. Not 180. 90 degrees more than flat geometry allows. That excess, called the angular excess, is a direct measure of the curvature of the surface. The bigger the triangle, the more excess it has. A tiny triangle near the equator might have angles summing to 180.1 degrees, barely noticeable. But the larger the triangle, the more the curvature reveals itself. This was the revolutionary idea of Carl Friedrich Gauss, the prince of mathematicians, in the early 1800s. He was surveying the kingdom of Hanover, measuring large triangles between mountain peaks, trying to detect whether our Earth's surface showed angular excess. And he did. Not much, because Earth is large, and the triangles he could measure were small relative to Earth's radius, but yes, the angle summed to slightly more than 180 degrees. He realized the geometry of physical space might not be Euclidean. And he kept this idea secret for decades, calling it Theorema Egregium, the remarkable theorem, because it showed that curvature is an intrinsic property. You don't need to step outside a surface to know it's curved. You just need to measure distances and angles within it. That leads us to Bernard Riemann, Gauss's brilliant student, who in 1854 gave a lecture that would change physics forever. His habilitation lecture, on the hypotheses which lie at the foundations of geometry, proposed that space itself might be multiplied curved, not just bent in one direction like a cylinder, but warped in complex ways, varying from point to point. He generalized geometry beyond flat planes and simple spheres to what we now call Riemannian geometry, the mathematics of curved spaces of any dimension. In Riemann's framework, a straight line is replaced by a geodesic, the shortest, or longest, path between 2 points in that space. On a flat plane, geodesics are straight lines. On a sphere, they're great circles. In a saddle-shaped surface, called hyperbolic, geodesics diverge, and parallel lines never meet, but there are infinitely many parallels through a point not on a given line. So now we have 3 geometries. Elliptic, like the sphere, no parallel lines, all geodesics intersect, triangle angles sum to more than 180 degrees. Euclidean, flat plane exactly one parallel line, triangle angles sum to exactly 180 degrees. Hyperbolic, saddle-shaped infinitely many parallels, triangle angles sum to less than 180 degrees. Which one is our universe? For centuries, we assumed Euclidean. After all, rooms are rectangular, tables are flat, surveyors use right angles, it all works. But Riemann dared to ask, what if space itself is curved? Not just the surface of the Earth, but three-dimensional space, or even four-dimensional space-time. Enter Albert Einstein. In 1915, Einstein published the general theory of relativity. And its core idea is deceptively simple: gravity is not a force. It's geometry. Massive objects, like stars, planets, black holes, don't pull on other objects with some invisible string. Instead, they warp the fabric of space-time around them. And objects, planets, light beams, even you, simply follow the straightest possible paths through that curved space-time. Those paths are geodesics. So when Earth orbits the Sun, it's not being tugged by a gravitational force. It's moving inertially, freely, without acceleration, along a geodesic in the curved space-time created by the Sun's mass. Think of it like rolling a marble around a funnel. The marble isn't being pulled inward by a force in the usual sense. It's just following the curve of the surface. The funnel is the gravity. This is where parallel lines come back in, dramatically. Imagine two particles, initially at rest relative to each other, floating in empty space far from any mass. Release them. In flat space-time, no gravity, they just stay put. Or if they're moving side by side with the same velocity, they remain parallel forever. Their world lines, paths through space-time, are parallel straight lines. Now bring in a massive object, say, Earth. Place those two particles side by side, high above the North Pole, both at rest relative to Earth. Release them. What happens? They both fall straight down toward the center of the Earth, along radial lines. At first, their paths are parallel, same height, same velocity, zero, same direction, down. But as they fall, their trajectories converge. Why? Because they're both aiming for the same point, Earth's center. In the curved space-time around Earth, the geodesics of freely falling objects bend toward each other. So two initially parallel geodesics, two straight paths in space-time, meet. Not because of a force acting between the particles, but because space-time itself is curved by mass. This convergence of geodesics is the geometric essence of gravity. We can quantify this with the geodesic deviation equation, a formula that tells us how the separation between two nearby geodesics changes as they move through curved space-time. Let me say that again. The geodesic deviation equation describes how initially parallel geodesics accelerate toward or away from each other due to curvature. In precise terms, suppose we have a family of geodesics, labeled by a parameter, say, s. Each geodesic is a path through space-time, parameterized by proper time t. Let x superscript a be the coordinates of a point on one geodesic. Then a nearby geodesic has coordinates x superscript a plus a small deviation vector, call it n superscript a. This deviation vector points from one geodesic to the other, like the distance between two falling particles. The geodesic deviation equation says the second derivative of n superscript a with respect to t, plus the Riemann curvature tensor with components a superscript a, subscript b c d, times the tangent vector to the geodesic u superscript b, times n superscript c, times u supersc. If d equals 0. Written out fully in words, not symbols, it is. the rate of change with respect to proper time of the rate of change with respect to proper time of the separation vector between two neighboring geodesics, plus the Riemann curvature tensor acting on the separation vector and the direction of motion equals 0. This equation is the mathematical embodiment of tidal gravity, the stretching and squeezing you'd feel if you fell feet first into a black hole. Your feet accelerate faster than your head, so you're stretched vertically, and your sides are pulled inward, so you're compressed horizontally. That's geodesic deviation in action. In the weak field limit, like near Earth, the Riemann tensor reduces to derivatives of the Newtonian gravitational potential, and the geodesic deviation equation becomes the acceleration of the separation vector equals the negative gradient of the gravitational field dotted with the separation vector. Or, more familiarly, the relative acceleration between two nearby freely falling particles equals minus the tidal tensor times the separation vector. The tidal tensor is just the matrix of second derivatives of the gravitational potential. For a point mass, its diagonal, two negative components, compression sideways, and one positive component, stretching radially. That's why the Moon creates two ocean tides on Earth, one on the side facing the Moon, one on the opposite side. The water on the near side is pulled more than Earth's center, the water on the far side is pulled less, so both bulge away from the center. Geodesics diverge in one direction, converge in the other. So, back to parallel lines. In the presence of mass, space-time curves. Geodesics, which are the straight lines of this curved geometry, can converge or diverge. Thus, initially parallel geodesics can meet. Or, in regions of negative curvature, like near certain exotic matter distributions, or in the early universe during inflation, they might diverge forever, hyperbolic behavior. But here's the subtlety: locally, space-time always looks flat. This is the equivalence principle, Einstein's happiest thought. If you're in a small, freely falling elevator, say, in orbit around Earth, you feel weightless. Dropped objects float beside you. Light beams travel in straight lines across the cabin. All experiments give the same results as in deep space, far from gravity. In that local patch, Euclidean geometry holds. Parallel lines don't meet. The laws of special relativity apply. But globally, over large distances, curvature reveals itself. Parallel geodesics do meet. So the answer to our title, why parallel lines can both meet and not meet, is this: it depends on the scale and the curvature of space-time. Locally, in a small enough region, space is flat, and parallels stay parallel. Globally, in the presence of mass energy, space is curved, and parallels can converge or diverge. That's not philosophy. That's engineering. Because this precise understanding of curved spacetime is what makes the global positioning system work. Let's talk about GPS. The GPS constellation consists of at least 24 satellites orbiting Earth at an altitude of about 20,000 kilometers, roughly twice Earth's radius. Each satellite carries multiple atomic clocks, extremely precise cesium or rubidium clocks, accurate to within a few nanoseconds per day. Why clocks? Because GPS works by timing. Your phone receives signals from at least 4 satellites. Each signal contains the exact time it was sent and the satellite's position at that moment. Your phone calculates the distance to each satellite by multiplying the signal travel time by the speed of light. Then, using trilateration, solving for the point in space that is exactly those distances from each satellite, it pinpoints your location on Earth. But here's the problem: time does not run at the same rate everywhere. According to special relativity, a moving clock runs slower than a stationary one. GPS satellites move at about 14,000 km per hour relative to Earth's surface, about 3.9 km per second. That's fast enough for time dilation to matter. The Lorentz factor gamma is 1 over the square root of 1 minus v squared over c squared. Plugging in v equals 3,900 meters per second, c equals 3 times 10 to the 8 meters per second, v squared over c squared is about 1.7 times 10 to the minus 10. So gamma is approximately 1 plus 8.5 times 10 to the minus 11. Which means the satellite clocks run slower by about 7 microseconds per day due to their motion. But according to general relativity, clocks in weaker gravitational fields run faster. GPS satellites are farther from Earth's center than we are, about 26,560 kilometers versus 6,371 kilometers at the surface. The gravitational potential is less negative up there, so time speeds up. The formula for gravitational time dilation in weak fields is the fractional rate difference equals delta phi over c squared, where delta phi is the difference in gravitational potential. The gravitational potential phi at distance r from Earth center is minus g times m Earth divided by r. So the potential difference between satellite and surface is g times m Earth times 1 over r surface minus 1 over r satellite. Plugging in g equals 6.674 times 10 to the minus 11, m Earth equals 5.972 times 10 to the 24 kilograms, our surface equals 6.371 times 10 to the 6 meters, our satellite equals 2.656 times t. N to the 7 meters, we get delta phi equals about 4.76 times 10 to the 7 joules per kilogram. Divide by c squared, 9 times 10 to the 16, and we get a fractional rate increase of about 5.3 times 10 to the minus 10. That means satellite clocks run faster by about 45 microseconds per day. Now combine both effects. Special relativity slows the clocks by 7 microseconds per day, general relativity speeds them up by 45 microseconds per day. Net effect, satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds. Doesn't sound like much. But light travels 300 million meters per second, so in 38 microseconds, light travels about 11.4 kilometers. If uncorrected, the timing error would cause positioning errors to accumulate at a rate of about 10 kilometers per day. Within 2 minutes, your GPS would be off by more than 100 meters. Within an hour, over 3 kilometers. It would be useless. So engineers pre-adjust the satellite clocks before launch. They set the fundamental frequency of the atomic clock slightly slower than their nominal value, specifically from 10.23 MHz to 10.22999995 for 3 MHz. That tiny offset compensates for the predicted relativistic drift. And it works. GPS accuracy is typically within 5 to 10 meters for civilian use, and under 1 meter with augmentation. But that's not all. GPS must also account for the curvature of spacetime in its calculations, not just time dilation, but the actual paths of signals. Radio signals from satellites travel along null geodesics, the straightest possible paths for light in curved spacetime. Near Earth, spacetime is well approximated by the Schwarzschild metric, the solution to Einstein's equations for a spherical, non-rotating mass. In Schwarzschild coordinates, the spacetime interval ds squared is equal to minus 1 minus 2 gm over c squared r times c squared dt squared, plus 1 minus 2 gm over c squared r to the minus 1 times dr squared, plus r squared times d theta squared, plus r squared t. I'm sine squared theta times d phi squared. But for signal propagation, we set ds squared equal to 0 for light, and solve for the travel time. The key point, light does not travel in Euclidean straight lines past a massive object. Its path is bent. This is gravitational lensing, first observed during the 1919 solar eclipse, confirming general relativity. For GPS, the bending is small, about 6 milliarcseconds for a signal grazing Earth's limb, but over 20,000 kilometers, it introduces a ranging error of about 2 centimeters. Small, but for high-precision applications, like surveying or aircraft landing, it must be modeled. Moreover, Earth rotates, so we must use the Kerr metric, not Schwarzschild, for full accuracy. Frame dragging, the twisting of spacetime by rotating mass, causes additional tiny shifts. The Gravity Probe B mission measured this in 2011, confirming predictions to within 19%. In GPS, frame dragging contributes a sub-centimeter effect, but again, for centimeter-level accuracy, it's included in modern models. So every time you tap your phone and see a little blue dot move smoothly down the street, you are witnessing a real-time validation of curved spacetime geometry. The system would fail catastrophically if engineers used Euclidean geometry and Newtonian time. It only works because we accept that parallel lines, geodesics in spacetime, behave differently depending on curvature. In the local frame of the satellite, light travels straight. In the global Earth-centered frame, its path is curved. Both descriptions are valid in their respective coordinate systems. That's the essence of general covariance. The laws of physics take the same form in all reference frames, but the geometry changes. Let's go deeper into the mathematics, not to intimidate, but to feel the structure. Einstein's field equations are the core of general relativity. In words, they state: the Einstein tensor equals 8 pi times the gravitational constant divided by the speed of light to the 4th power, multiplied by the stress energy tensor. The Einstein tensor, G subscript mu nu, encodes the curvature of spacetime. It is defined as the Ricci curvature tensor minus 1/2 the spacetime metric times the Ricci scalar. The Ricci tensor, R subscript mu nu, is a contraction of the Riemann curvature tensor, summing over 2 indices. It measures how the volume of a small cloud of test particles changes as it moves along geodesics. The Riemann tensor, R superscript rho subscript sigma mu nu, is built from the Christoffel symbols, the connection coefficients that tell you how to parallel transport vectors in curved space, and their derivatives. A Christoffel symbol, gamma superscript rho subscript mu nu, equals 1/2 the inverse metric times the partial derivative of the metric with respect to x superscript mu, plus the partial derivative with respect to x superscript nu, minus the partial derivative with respect to x superscript rho. The metric tensor, G subscript mu nu, is the fundamental object. It tells you how to compute distances and angles. In flat spacetime, in Minkowski space, it's diagonal, -1, +1, +1, +1, for time and 3 space dimensions. But near a mass, it distorts. For example, in Schwarzschild coordinates, the time component of the metric is -1 - 2 gm over c squared r. As r approaches 2 gm over c squared, the Schwarzschild radius, the metric component goes to 0. That's the event horizon of a black hole. At that point, the roles of time and space swap. The radial coordinate becomes time-like. You must move inward, just as you must move forward in time in flat space. That's why nothing escapes a black hole. All future-directed geodesics lead to the singularity. Now, consider 2 light rays, parallel at infinity, passing on opposite sides of a black hole. Due to extreme curvature, their geodesics bend so much that they cross. In fact, around a black hole, you can have photon spheres, orbits where light circles forever at r equals 3 gm over c squared. And multiple images, light from a single star can take different paths around the black hole and reach you from multiple directions. So parallel light rays not only meet, they can loop, intersect, and create infinite Einstein rings in ideal cases. But let's return to something gentler, Earth's surface. We already saw that on a sphere, parallel lines meet. But Earth isn't a perfect sphere, it's an oblate spheroid, flattened at the poles due to rotation. The equatorial radius is about 21 kilometers larger than the polar radius. That means the curvature isn't uniform, it's stronger at the poles than at the equator. How does that affect geometry? Take two lines of longitude again, they still meet at the poles. But now consider two lines of latitude. Are they parallel? On a perfect sphere, all lines of latitude except the equator are not geodesics, they are smaller circles. A geodesic on Earth's surface is a great circle route, like the one airplanes use between distant cities. But suppose we define a parallel as constant separation. On Earth's oblate surface, two lines of latitude, say, 40 degrees north and 41 degrees north, maintain nearly constant distance. But not exactly. Because the meridians converge less rapidly near the equator than near the poles, due to flattening, the distance between latitudes varies slightly with longitude. In precise geodesy, this is modeled using the ellipsoidal Earth model, like WGS-84, the standard for GPS. In WGS-84, the Earth is approximated as an ellipsoid with semi-major axis A equals 6,378,137 meters, and flattening F equals 1 over 298.2572235363 e. From that, you compute the radius of curvature in the prime vertical and meridian, and then solve the geodesic differential equations to find the shortest path between 2 points. Those equations are non-linear and must be solved numerically. But the result is clear: even on Earth, straight lines curve in 3D space, and parallel lines behave in complex ways, depending on direction, location, and scale. Which brings us to cosmology, the geometry of the entire universe. Is the universe flat? Spherical? Saddle-shaped? We don't know for certain, but observations strongly suggest it's very close to flat, on large scales. The Planck satellite measured the cosmic microwave background, the afterglow of the Big Bang, and found that the angles of giant triangles formed by temperature fluctuation sum to 180 degrees, within a margin of error of about 0.2%. That implies the universe's spatial curvature is nearly zero. But nearly flat isn't the same as exactly flat. And even if space is flat, space-time is curved by the matter and energy within it. The Friedmann-Lemaitre-Robertson-Walker metric describes a homogeneous, isotropic universe. Its spatial part can have three curvatures. Positive curvature, K equals +1 closed universe, finite volume, like a 3D sphere. Parallel geodesics converge. Eventually, a light beam could circumnavigate the universe and return to its start. Zero curvature, K equals 0 flat, infinite universe. Parallel geodesics remain parallel, Euclidean. Negative curvature, K equals -1 open, infinite, hyperbolic universe. Parallel geodesics diverge. The dynamics are governed by the Friedmann equations. The square of the Hubble parameter equals 8 pi g over 3 times the energy density, minus kc squared over a squared, plus lambda c squared over 3. And the second derivative of the scale factor a with respect to time, divided by a, equals -4 pi g over 3 times energy density plus 3 times pressure over c squared, plus lambda c squared over 3. Here, lambda is the cosmological constant, Einstein's greatest blunder, which he later retracted, but which we now know drives the accelerated expansion of the universe. Dark energy, modeled by lambda, acts like a constant energy density of the vacuum. Its pressure is negative P equals -ρ c squared. Plug that into the second Friedmann equation, energy density plus 3p over c squared equals ρ minus 3ρ equals -2ρ, so the acceleration term becomes positive. the universe expands faster and faster. What does that do to parallel lines? In an accelerating universe, distant galaxies recede faster and faster. Eventually, light emitted today from a galaxy beyond a certain distance, the cosmic event horizon, will never reach us. The space between us and that galaxy expands faster than light can traverse it. So too photons emitted parallel toward us from such a galaxy will never meet us, they'll be carried away by expansion. But locally, within galaxy clusters, bound by gravity, space isn't expanding. The Milky Way and Andromeda are moving toward each other. In those regions, geodesics can still converge. So again, parallel lines can meet, in bound systems, or never meet, in the accelerating void between superclusters. Both are true, depending on where and when you look. Let's consider a concrete experiment you can almost do at home. Take two laser pointers. Mount them perfectly parallel on a rigid bar, say, 1 meter apart. Shine them across a large room. On a flat floor, the dots stay 1 meter apart. But if you could shine them over a very large distance, say, across a mountain valley, you'd see the dots move closer together. Not because the lasers bend, but because Earth's surface curves downward. After 5 kilometers, the Earth drops by about 2 meters. If your lasers are at eye level, the dots would hit the ground unless aimed slightly upward. But more subtly, even in vacuum, if you could fire 2 parallel laser beams past the Sun, they would converge slightly due to space-time curvature. The deflection angle is 4 gm/c²r for the Sun, about 1.75 arcseconds. So 2 beams skimming opposite sides of the Sun would each bend toward the center by that amount, meaning their paths converge by about 3.5 arcseconds. Over astronomical distances, that leads to multiple images, arcs, and rings, gravitational lenses. Astronomers use this as a tool. By measuring how light bends around galaxy clusters, they map the total mass, including dark matter, which doesn't emit light but does curve space-time. The Bullet cluster is the classic example. Visible matter, hot gas, collided and slowed down, but the gravitational lensing map shows mass offset from the gas, proof that most mass is dark and collisionless. So parallel light rays, initially parallel, are bent by invisible mass. They meet, or appear to originate from different points. Geometry reveals what light cannot. Now, let's return to the equivalence principle, the idea that gravity and acceleration are locally indistinguishable. Imagine you're in a rocket ship, far from any stars, accelerating at 9.8 meters per second squared, Earth's gravity. You stand on the floor. Drop a ball, it falls to the floor at 9.8 meters per second squared. Shine a laser horizontally across the cabin, the beam appears to curve downward because the floor is accelerating upward to meet it. In your reference frame, light bends in a gravitational field. But in an inertial frame, outside the rocket, the light travels straight. The floor moves up. So the appearance of bending depends on your frame. Now replace acceleration with gravity. In a stationary lab on Earth, light also bends downward, by the same amount. Einstein predicted this, and Eddington confirmed it in 1919. So are the light rays parallel? In the inertial frame, yes, initially. But spacetime is curved, so their geodesics converge. In the Earth frame, no, they're curved paths. Both are correct descriptions. This is why general relativity uses tensor equations. They are covariant, meaning they hold in any coordinate system. The physics is invariant, only the description changes. Let's talk about parallel transport, a key concept for understanding curvature. Imagine walking on Earth, holding an arrow pointing north. Start at the equator, 0 degrees longitude. Walk north to the North Pole, keeping the arrow pointing in the same direction relative to your path, That's parallel transport. When you reach the pole, your arrow points along the 180-degree meridian, south, toward the international date line. Now walk south along the 90 degrees west meridian, still parallel transporting the arrow. It now points west, perpendicular to your path. Finally, walk east along the equator back to your start. The arrow now points south, not north, where you began. You've returned to the starting point, but the arrow has rotated by 90 degrees. That's holonomy, a direct measure of curvature. On a flat plane, parallel transport around a loop brings the vector back unchanged. On a sphere, it rotates by an amount equal to the solid angle enclosed by the loop. For our triangle, North Pole, 0, 90 east, the solid angle is 1/8 of the sphere, or pi over 2 steradians. And indeed, the arrow rotated by 90 degrees, pi over 2 radians. This is how curvature manifests, failure of parallel transport to be path-independent. In general relativity, the Riemann tensor quantifies this. Its components tell you how much a vector changes when parallel transported around an infinitesimal loop. So when we say parallel lines meet, we're really talking about how direction itself is defined in curved space. There's no global notion of same direction, only local. Two lines can be parallel at one point, but not at another, because the meaning of parallel evolves as you move. That's why in curved space, you can't define a global Cartesian grid. Coordinates are just labels, they don't correspond to physical distances unless you use the metric. For example, in Schwarzschild coordinates, the radial coordinate r is not the physical distance to the center. The proper distance is the integral of dr over the square root of 1 minus 2 gm over c squared r to the minus 1. So between r equals 2rs and r equals 3rs, the proper distance is greater than rs, space is stretched radially near a black hole. Similarly, time coordinate t is not proper time. A clock at rest at radius r ticks at a rate of square root of 1 minus 2 gm over c squared r times dt. So deeper in the gravity well, clocks tick slower. All of this is necessary to answer our original question, not just who can parallel lines meet, but how, where, and why it matters. Let me summarize where we are. On a flat plane, parallel lines never meet. Triangle angles sum to 180 degrees. Space-time is Minkowskian. GPS would fail without relativity corrections. On a sphere, parallel lines, at a point, can meet. Triangle angles exceed 180. Geodesics converge. Earth's surface is approximately spherical, great circle roots prove it. In hyperbolic space, parallel lines diverge. Triangle angles sum to less than 180. The universe might have been hyperbolic in its earliest moments. In general relativity, space-time curvature, caused by mass energy, makes geodesics converge, gravity, or diverge, dark energy. Parallel transport rotates vectors. Clocks tick at different rates. Light bends. And crucially, all of these are valid geometries. None is more true than the others, each describes a possible universe, or a region within ours. Now, let's consider a thought experiment Einstein loved, the rotating disk. Imagine a disk spinning at constant angular velocity. An observer on the disk tries to measure its circumference and radius with rulers. Due to special relativity, rulers along the edge are Lorentz contracted, shortened in the direction of motion. So to cover the circumference, you need more rulers than in the non-rotating case. But rulers pointing radially are not contracted, they're perpendicular to motion, so the radius measurement is unchanged. Thus, circumference divided by diameter is greater than pi. The spatial geometry, as measured by the rotating observer, is non-Euclidean. In fact, it's hyperbolic. But why? Because acceleration, rotation, is equivalent to gravity, and gravity curves space. Einstein realized that if acceleration distorts geometry, then gravity must be geometry. This was the bridge from special to general relativity. The rotating disk shows that even in flat spacetime, non-inertial observers experience effective curvature. But in general relativity, we absorb that into the metric. We describe everything from the perspective of freely falling frames, where spacetime is locally flat. So the moral is, curvature is not just bending into a higher dimension. It's intrinsic, measurable by angles, distances, and parallel transport. And it governs motion. Let's derive, gently, the geodesic equation. A geodesic is the path that extremizes proper time for massive particles, or affine parameter, for light. For a massive particle, proper time tau is the integral of ds over c, where ds squared is the spacetime interval. To find the path that maximizes tau between two events, we use the calculus of variations. The Lagrangian is L equals 1/2 g subscript mu nu times dx superscript mu over d tau times dx superscript nu over d tau. The Euler-Lagrange equation says d over d tau of partial L over partial dx superscript rho over d tau equals partial L over partial x superscript rho. Computing that gives d over d tau of g subscript rho nu times dx superscript nu over d tau equals 1/2 partial g subscript mu nu over partial x superscript rho times dx superscript mu over d tau times dx superscript nu over d tau. Expanding the left side using the product rule. G subscript rho nu times d squared x superscript nu over d tau squared plus partial g subscript rho nu over partial x superscript mu times dx superscript mu over d tau times dx superscript nu over d tau. Now subtract the right side and rearrange. After symmetrizing indices, we get d squared x superscript rho over d tau squared plus gamma superscript rho subscript mu nu times dx superscript mu over d tau times dx superscript nu over d tau equals 0. That's the geodesic equation. It says, the second derivative of position plus connection terms equals 0. In flat space, gamma is 0, and we get straight lines, d squared x over d tau squared equals 0. In curved space, gamma is non-zero, and the path accelerates, but this acceleration is inertial motion. There's no force, just geometry. So when you stand on Earth, you feel a force, but in free fall, you don't. Your geodesic is curved in space-time, but straight in the local sense. Now, return to parallel lines. Suppose we have two geodesics, infinitesimally close. Let their separation be n superscript rho. Then the relative acceleration is given by the geodesic deviation equation, as we said earlier. In a weak, static gravitational field, like Earth's, the dominant component of the Riemann tensor is our superscript 0 subscript I0 j equals partial squared phi over partial x superscript I partial x superscript j, where phi is the Newtonian potential. So for two particles separated in the x direction, the relative acceleration in x is minus partial squared phi over partial x squared times n superscript x. For a point mass, phi equals minus gm over r. In Cartesian coordinates, at a point on the x-axis, partial squared phi over partial x squared equals 2gm over r cubed, and partial squared phi over partial y squared equals partial squared phi over partial z squared equals minus gm over r cubed. So acceleration in x, minus 2gm over r cubed times nx, stretching. Acceleration in y, plus gm over r cubed times ny, or squeezing. Same for z. That's the tidal tensor. And it's why the moon pulls the oceans into two bulges. So, parallel geodesics diverge in one direction, converge in the others. They don't just meet, they distort. This is measurable. The LISA mission, Laser Interferometer Space Antenna, will use 3 spacecraft in a triangular formation, 1 million kilometers apart, firing lasers between them. As gravitational waves pass, they alternately stretch and squeeze spacetime, changing the distances by picometers. LISA will detect supermassive black hole mergers across cosmic time by watching parallel laser beams change their separation. Gravitational waves are ripples in spacetime curvature. They cause geodesics to oscillate, parallel lines rhythmically converge and diverge. So in a gravitational wave, parallel lines both meet and not meet, cyclically, at the frequency of the wave. That's poetic, and true. Let's consider black holes again, more carefully. At the event horizon, r equals 2gm/c², the Schwarzschild radius. For the Sun, that's about 3 kilometers. For Earth, about 9 millimeters. If you compressed Earth to the size of a marble, it would become a black hole. But the singularity, the point of infinite density, is not a point in space. It's a moment in time. Inside the horizon, the radial coordinate becomes timelike, so falling to r equals 0 is as inevitable as tomorrow arriving. What happens to parallel lines there? As two particles fall toward the singularity, tidal forces grow without bound. The relative acceleration goes as gm/r³ times separation. As r approaches 0, this blows up. So initially parallel geodesics are violently distorted, spaghettified. But before that, near the horizon, something strange happens with light. Photons can orbit at r equals 3gm/c², the photon sphere. If you shine a laser exactly tangent to this sphere, it circles forever. Slightly inward, it falls in, slightly outward, it escapes. So two photons emitted parallel, one just inside and one just outside the photon sphere, will have drastically different fates, one captured, one free. Parallel lines, one meets the singularity, one doesn't. And if you're falling in, you'd see the entire future history of the universe blue-shifted and sped up in the last moments, because light from outside catches up to you as you approach the singularity. But that's a story for another night. Let's come back to Earth, and to you. When you lie in bed tonight, you are not at rest. You're rotating with Earth, about 460 meters per second at the equator. You're orbiting the Sun, 30 kilometers per second. The Sun orbits the galactic center, 230 kilometers per second. The galaxy moves toward Andromeda, 110 kilometers per second. And the whole local group falls toward the Great Attractor, over 600 kilometers per second. Your world line through spacetime is a complex, spiraling geodesic, bent by the Sun, the galaxy, the cosmic web. And yet, locally, you feel still. Your room is flat. Parallel lines on your ceiling never meet. That's the miracle of general relativity. The universe is wildly curved on large scales, but smoothly curved, so that in every small patch, physics is simple, local, and flat. Einstein called this the happiest thought of my life, that a falling person feels no gravity. From that seed grew a theory that redefined space, time, matter, and motion. And it all starts with a question about parallel lines. So tonight, as you drift off, picture two lines, drawn on an orange, on a saddle, in the void between galaxies. Watch them run side by side. See them stay parallel, in a small room, in deep space. Then watch them bend, toward a star, around a black hole, across the expanding cosmos. See them meet at a pole, diverge in a void, oscillate in a wave. They are not contradicting each other. They are responding to the shape of the world they inhabit. Geometry is not fixed. It is dynamic. It is physical. It is alive. And you are moving through it every second on a geodesic of your own. So rest now. Let your thoughts follow the curve of space-time. It's smooth, gentle, inevitable. The universe is not flat. It is not rigid. It breathes. It bends. It connects. And somewhere, in the dark, two parallel lines are meeting, just as they always do, and never do. You are safe. You are falling. You are free. And so, as you breathe in and out, let's return, not to the end, but to the center, where two particles float, side by side, in the quiet dark. They are not moving. Not yet. Their world lines are parallel, perfectly aligned in space-time, like two strands of silk suspended in still air. Now a star forms. Far away at first. Its mass whispers into the fabric around it, a soft curvature, barely a ripple. The particles feel nothing. Locally, their space is still flat. A ruler between them reads the same. A laser beam shot from one to the other travels straight and true. But as the star grows, collapsing, igniting, burning, the curvature deepens. The whisper becomes a hum. And that hum is encoded in a Riemann tensor, a set of numbers at every point, telling spacetime how to bend. Let's say the star has mass m. Let the particles be separated by a small distance s, perpendicular to the line toward the star. Let their distance from the star's center be r. Then, the relative acceleration between them, the rate at which their separation changes, is given by the relative acceleration equals the gravitational constant g times the mass m times the separation s, all divided by the distance r cubed. Written fully, relative acceleration equals g times m times s divided by r raised to the third power. This is the tidal acceleration. It is not a force pulling the particles apart. It is the geometry of their free fall. Each particle follows its own straightest path, a geodesic, in curved spacetime. And because spacetime is curved differently at slightly different locations, those geodesics diverge. If the separation s is radial, along the line toward the star, then the relative acceleration is twice as large, and in the opposite direction. Relative acceleration equals -2 times g times m times s divided by r cubed. Negative sign means they accelerate toward each other, convergence. So in 3 dimensions, the tidal field is a stretching in one direction, squeezing in the other two, like pulling on a rubber band while compressing it sideways. This is why, if you fell feet first into a black hole, your body would be pulled apart, your feet feeling stronger gravity than your head, while your sides were gently pressed inward. Not by any mechanical grip, but by the pure shape of spacetime. Now, imagine you could see spacetime curvature, not as numbers, but as light. There is a way. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime for the first time. 2 black holes, 29 and 36 times the mass of our Sun, spiraled inward and merged 1.3 billion light-years away. In the final fraction of a second, they released more power in gravitational waves than all the stars in the observable universe combined. And here on Earth, in 2 L-shaped vacuum tunnels, for kilometers long, the passing wave changed the length of the arms by less than 1/10,000th the width of a proton. How? By altering the geodesics of the laser beams inside. Each arm holds a laser beam bouncing between mirrors. When the arms are exactly equal length, the light waves cancel out, destructive interference, and the detector sees darkness. But when a gravitational wave passes, it alternately stretches one arm while squeezing the other, then vice versa, quadrupole deformation. The geodesics of the light shift. The travel times change. The interference pattern flickers. That flicker is the sound of space-time ringing. And in that signal, encoded in the waveform, we read the masses, spins, distance, and orbital dynamics of the colliding black holes. Crucially, gravitational waves are transverse. They have two polarizations, plus and cross. In the plus polarization, space stretches along one axis while compressing along the perpendicular axis, like our tidal field. In the cross polarization, the same happens, but rotated by 45 degrees. So if you placed a ring of freely floating particles in space, a plus-polarized wave would distort it into an ellipse, first tall and narrow, then short and wide, oscillating back and forth. The particles never move through space. They stay at rest relative to their local inertial frame. But the space between them breathes. And their world lines, initially parallel, now rhythmically converge and diverge. Meet, not meet, meet again, not meet. Like a slow, cosmic heartbeat. This is not metaphor. This is measurement. LIGO has now observed over 90 such events, black holes, neutron stars, possibly hybrid mergers, each one a direct observation of dynamic space-time curvature. And soon, the Laser Interferometer Space Antenna, LISA, will fly. 3 spacecraft, forming a triangle 1 million kilometers on a side, trailing Earth in its orbit around the Sun. LISA will detect lower frequency waves, waves from supermassive black holes, millions to billions of solar masses, merging in the centers of galaxies. As those waves pass, the distances between the spacecraft will change by picometers, trillionths of a meter. To measure that, LISA fires lasers between the craft and monitors the phase of the light. But here's the subtlety: the lasers don't travel through flat space. They follow null geodesics in the curved spacetime of the solar system. So the data analysis must account for Shapiro delay, the extra time light takes when passing near the Sun, due to spacetime curvature. Light bending, the apparent position of one spacecraft shifts as its signal grazes the Sun. Gravitational redshift, clocks on the spacecraft tick at slightly different rates depending on their position in the Sun's gravity well. All of these are relativistic corrections applied in real time. If ignored, LISA's sensitivity would be ruined. So again, we see it: parallel laser beams, sent across interplanetary space, do not behave as Euclid would predict. Their travel times, paths, and phases encode the curvature of spacetime itself. Now, let's go smaller. Not to stars or black holes, but to Earth's surface. To a surveyor standing on a hill, aiming a theodolite. A theodolite measures horizontal and vertical angles with extreme precision, down to 1 arcsecond. To map a city, a mountain range, a tunnel for a particle accelerator, surveyors must account for Earth's curvature. For example, over a distance of 1 kilometer, the Earth's surface drops by about 7.8 centimeters relative to a straight line. Over 10 kilometers? 7.8 meters. So if 2 survey markers are placed 1 kilometer apart at the same elevation, and you sight horizontally from one to the other, your line of sight passes above the midpoint of the ground by nearly 2 centimeters, because the ground curves away. Surveyors correct for this using the formula. Drop equals distance squared divided by 2 times Earth's radius. With Earth's mean radius r equals 6,371,000 meters, for distance d in meters, drop in meters is d squared divided by 12,742,000. So for d equals 1,000, drop equals 1 million divided by 12,742,000, almost equal to 0.0785 meters, 7.85 centimeters. But that's for a sphere. Earth is an ellipsoid, so the radius of curvature changes with latitude. The radius of curvature in the meridian, north-south, is smaller at the poles, larger at the equator. It is given by a times 1 minus eccentricity squared divided by 1 minus eccentricity squared times sine squared latitude raised to the 3/2 power. Where a is the equatorial radius, an eccentricity squared is about 6.69 for 38 times 10 to the minus 3. Similarly, the radius of curvature in the prime vertical, east-west, is a divided by the square root of 1 minus eccentricity squared times sine squared latitude. So a surveyor in Oslo must use slightly different curvature corrections than one in Quito, even for the same distance, because the local geometry is different. And when they compute the shortest path between 2 points, the geodesic, they solve the inverse geodesic problem, given latitude and longitude of point 1 and point 2, find the distance and forward azimuth. This is done using algorithms like Vincente's formulae, iterative methods that converge to millimeter accuracy on the WGS84 ellipsoid. Vincente's method starts with an initial guess for the reduced latitude, then refines it using the flattening and eccentricity, computing integrals of the radius of curvature along the path. Why go to such lengths? Because for projects like the Large Hadron Collider, 27 kilometers in circumference, the tunnel must be aligned so that proton beams, traveling at 99.999999% of light speed, stay centered for hours. A curvature error of 1 part in 10 million would cause the beam to scrape the wall. So geometry, non-Euclidean, ellipsoidal, relativistic geometry, is built into the bedrock of modern science. Even your phone uses it. When you open a map app, your position is computed not just from satellite timing, but from ephemeris data, precise tables of where each GPS satellite actually is, accounting for solar radiation pressure pushing on the satellite body, Earth's gravitational field anomalies, mountains, ocean trenches, mantle plumes that perturb orbits, relativistic effects. The satellite's orbits themselves are geodesics in Earth's curved spacetime, described by the post-Newtonian equations of motion. The standard model for GPS satellite motion includes terms like the acceleration vector equals minus gm Earth times the position vector divided by r cubed, plus 2 gm Earth over c squared r times 4 gm Earth over r minus v squared times the position vector divided by rc cubed, plus 4 gm Earth over c squared r cubed times position vector dot velocity vector times velocity vector, plus other smaller terms for Earth's arblateness, third body gravity, moon, sun, and tides. Each term is a correction to Newton's inverse square law or derived from Einstein's field equations in the weak field limit. Without these, satellite orbits would drift by kilometers per year. GPS would fail. So when you see your blue dot glide smoothly along a street, you are seeing general relativity in real time, a fusion of curved geometry, precise timekeeping, and orbital mechanics. Now, let's consider time, not just as a coordinate, but as something that flows at different rates. We've spoken of clocks running faster on satellites. But what about you? Your head is farther from Earth's center than your feet, by about 1.7 meters, if your average height. So your head ages faster than your feet. How much? Using the weak field formula, fractional time difference equals g times height difference divided by c squared, where g is 9.8 meters per second squared, height is 1.7 meters, c is 3 times 10 to the 8 meters per second. So delta tau over tau equals 9.8 times 1.7, divided by a 9 times 10 to the 16, almost equal to 1.85 times 10 to the minus 16. Over 70 years, about 2.2 billion seconds, your head ages more than your feet by 2.2 times 10 to the 9 seconds times 1.85 times 10 to the minus 16 almost equal to 4.07 times 10 to the minus 7 seconds. About 400 nanoseconds. Not enough to notice, but measurable. In 2010, the National Institute of Standards and Technology compared two atomic clocks, one raised just 33 centimeters above the other. The higher clock ran faster by 4 parts in 10 to the 17, exactly as predicted. So even within your body, space-time is curved. Parallel world lines, your heads and your feet, diverge in time. They do not meet. They accumulate separation. Yet you feel whole, unified. Because the divergence is tiny, and your nervous system averages over milliseconds, not nanoseconds. But the geometry is there, in your bones, in your blood, in the quiet pulse of your cells. Now, imagine a universe where curvature is not gentle, where it dominates. In the first fraction of a second after the Big Bang, the universe was unimaginably dense. Energy densities exceeded 10 to the 94 grams per cubic centimeter. Space-time curvature was extreme. Quantum effects, normally negligible, became significant. And here, general relativity breaks down. It is a classical theory. It does not include quantum uncertainty. So we need a theory of quantum gravity. We don't have a complete one yet. But we have clues. One idea is loop quantum gravity. It proposes that spacetime is not smooth, but woven from finite loops, quantized areas and volumes. The smallest possible area is about the Planck length squared, 10 to the minus 70 meters squared. In this picture, the Big Bang singularity is replaced by a big bounce, a previous contracting phase rebounding into our expansion. Geodesics do not end, they pass through. Parallel lines, in such a granular spacetime, might behave strangely at the tiniest scales, fluctuating, foaming, losing definite direction. Another idea is string theory. It posits that fundamental particles are vibrating strings, and that spacetime may have extra dimensions, curled up at microscopic scales. In string theory, gravity emerges from the exchange of closed strings. And the geometry of those extra dimensions determines the laws of physics we see, like the masses of electrons or the strength of forces. So curvature isn't just in spacetime, it is spacetime, and possibly more. But even without knowing the final theory, we can test quantum aspects of gravity. In 2017, researchers at the University of Southampton placed a tiny glass sphere, just 100 nanometers across, into a quantum superposition of two locations, separated by less than the width of a DNA strand. They then asked, does the sphere's own gravitational field cause decoherence? Does spacetime curvature respond to a quantum source? This is the frontier, quantum superpositions of geometry. If two masses are in superposition, say, left and right, does the spacetime around them also enter superposition? Do geodesics split? Do parallel lines branch? We don't know yet. Experiments are underway. But the question, can parallel lines meet and not meet, takes on a new depth. In quantum gravity, the answer might be both at once. Now, let's return to navigation, not on land, but under the sea. Submarines cannot use GPS. Radio waves do not penetrate seawater. So they navigate inertially, using gyroscopes and accelerometers. An inertial navigation system, INS, starts with a known position. Then it integrates acceleration to get velocity, and velocity to get position. But accelerometers do not measure coordinate acceleration. They measure proper acceleration, deviation from free fall. When the submarine is at rest on the ocean floor, its accelerometer reads 9.8 meters per second squared upward, because the floor is pushing it off its geodesic. To compute true motion, the INS must subtract Earth's gravity and Earth's rotation. The effective gravity vector includes gravitational attraction toward Earth's center, centrifugal force due to rotation, outward, perpendicular to the axis, Coriolis force, if the sub is moving, the rotation of Earth deflects its path. The Coriolis acceleration equals -2 times the angular velocity vector of Earth crossed with the velocity vector of the submarine. Earth's angular velocity is 7.2921 times 10 to the -5 radians per second. So for a submarine moving east at 10 meters per second at 45 degrees latitude, the Coriolis acceleration is about 1.03 millimeters per second squared, small, but over hours, it causes kilometers of error. High-end INS units use Stühler tuning, a feedback loop that makes the system oscillate with a period of 84.4 minutes, matching the natural period of a pendulum whose length is Earth's radius. Why? Because if the INS platform tilts by a small angle, the error in gravity direction causes a position drift that grows quadratically unless tuned. Stühler tuning converts that into a bounded oscillation. This tuning only works because Earth is approximately spherical. On a flat Earth, Stühler tuning would be meaningless. So even in the crushing dark of the deep ocean, submarines rely on the curvature of the Earth to navigate accurately. And when they surface and get a GPS fix, the two systems, INS and GPS, are fused using a Kalman filter which weights each based on estimated uncertainty, continuously correcting for drift. The Kalman filter equations involve a state vector, position, velocity, attitude errors, a dynamics matrix that includes Earth's rotation and curvature terms, a measurement matrix for GPS pseudo-ranges, covariance updates based on process and measurement noise. All of it, every matrix entry, is shaped by non-Euclidean geometry. Now, let's speak of history, not as dates, but as ideas unfolding. For 2,000 years, Euclid's geometry was truth. The parallel postulate was a self-evident axiom. But in the early 1800s, three men, working independently, dared to imagine otherwise. Nikolai Lobachevsky in Russia, János Bolyai in Hungary, and Carl Friedrich Gauss in Germany. Lobachevsky published first, in 1829, in Russian, titled On the Principles of Geometry. He assumed that through a point not on a line, more than one parallel could be drawn. He derived a consistent geometry, hyperbolic, where triangles have angle sums less than 180, and the circumference of a circle grows faster than 2 pi r. Bolyai, in an appendix to his father's book, wrote, "Out of nothing I have created a strange new universe." Gauss, cautious, never published, but in letters, he confessed he believed in non-Euclidean geometry for decades. When Bolyai's work reached him, he wrote, "To praise it would amount to praising myself." Why did they doubt Euclid? Because the parallel postulate felt different. The first four postulates are constructive: draw a line, extend a segment, describe a circle. The fifth is global, conditional, complex. Gauss tested it empirically. As director of the Göttingen Observatory, he measured the triangle between three mountain peaks, Brocken, Hoher-Hagen, and Inselsberg. The sum of angles was 179 degrees 59 minutes 59.3 seconds, within error of 180. He concluded space was flat, at that scale. But he knew the question remained open. Then came Riemann, Gauss's student. In his 1854 lecture, he proposed that space could have variable curvature, positive here, negative there, described by a metric tensor. He imagined beings living on a surface, discovering their world shaped through internal measurements. And he ended with a profound statement: the properties which distinguish space from other conceivable triply extended manifolds can only be deduced from experience. Geometry is not logic. It is physics. Einstein read Riemann. He worked with Marcel Grossmann, who introduced him to Ricci and Levi Civita's tensor calculus. For years, Einstein struggled. He tried scalar theories, then vector theories. Only when he embraced generally covariant tensor equations did the pieces fall. In November 1915, he presented the final field equations to the Prussian Academy. Within days, he applied them to Mercury's orbit, explaining its anomalous precession of 43 arcseconds per century, unexplained by Newton. Space was curved. Geometry was gravity. And parallel lines? In the space-time around the Sun, the geodesics of planets precess, their ellipses rotate slowly, because that straight lines are not closed. Mercury's perihelion advances, not because of another planet, but because it moves through curved space. So even in our solar system, parallel lines do not behave as in Euclid's world. Now, let's consider light, not just bending, but delaying. In 1964, Erwin Shapiro proposed a new test of general relativity, radar echo delay. Send a radar pulse to a planet, say Venus, when it is on the far side of the Sun. Measure the round-trip time. According to Newton, the time should be 2 times the distance divided by c. But according to Einstein, as the signal passes near the Sun, it travels through deeper gravitational potential, where time runs slower and space is stretched. So the light takes longer. The extra delay is approximately for gm Sun over c cubed times the natural logarithm of for times our Earth times a Venus divided by our Sun squared. For superior conjunction, when Venus is behind the Sun, the delay is about 200 microseconds. Shapiro measured it using the MIT Haystack Observatory and later the Viking landers on Mars. The results matched general relativity to within 1%. So not only do light rays bend, they also slow down in coordinate time, though locally, they always move at c. This is key. The speed of light is constant locally, in inertial frames. But globally, in curved coordinates, the coordinate speed of light can vary. Near a black hole, the radial coordinate speed of light is c times 1 minus 2 gm over c squared r. At the horizon, it drops to 0. Light appears to freeze, though for the photon itself, proper time doesn't pass. So 2 parallel light beams, falling toward a black hole, appear to slow down and redshift, converging as they approach the horizon. To a distant observer, they never quite cross it. To an infalling observer, they do, smoothly, in finite time. Both are correct. Perspective matters. Geometry is relational. Now, let's speak of frames, not as abstractions, but as lived experience. You are lying in bed. Your reference frame is accelerating upward at 1 g because the mattress pushes you off your geodesic. In your frame, gravity is a force. Objects fall. Light bends. But if the floor vanished, free fall, you'd float. Gravity would disappear. Light would go straight. So which is real? Neither. Both are valid coordinate systems. General relativity says, the laws of physics must be expressible in any coordinates. The Einstein tensor transforms covariantly. The field equations hold everywhere. This is general covariance, not just a mathematical trick, but a physical principle. There are no privileged observers. The universe does not care whether you are spinning, falling, or floating. It only cares about relationships between events, between world lines, between geodesics. And in those relationships, curvature manifests. Now, consider 2 astronauts, far from any mass, floating in deep space. They are at rest relative to each other. Their geodesics are parallel. Now one turns on a rocket, briefly, giving themselves a small velocity perpendicular to the line between them. After the burn, they coast. Their world lines are now straight but diverging in spacetime, like two lines on a flat plane with a small angle between them. They will drift apart forever. But if, instead, a planet appears between them, without either firing engines, their geodesics curve toward each other. They may meet. Same initial separation. Same initial relative velocity, 0. Different outcomes, depending on the geometry. So motion is not caused by forces alone. It is shaped by the stage on which it plays. Space-time is not a container. It is an actor. And its script is written in tensors. Let's name them, not to memorize, but to feel their weight. The metric tensor G mu nu, 10 independent components. It tells you how to measure intervals. The Christoffel symbols gamma rho mu nu, 40 independent components, in 4 dimensions. They tell you how vectors change under parallel transport. The Riemann tensor are rho sigma mu nu, 20 independent components. It tells you the full curvature, tidal forces, geodesic deviation, holonomy. The Ricci tensor are mu nu, 10 components. Contraction of Riemann appears in the field equations. The Ricci scalar are 1 number. Contraction of Ricci measures average curvature. The Einstein tensor G mu nu equals a mu nu minus 1/2 G mu nu r. And this equals 8 pi G over c to the 4th times T mu nu, the stress energy tensor. T mu nu includes energy density, momentum density, pressure, shear stress. So mass energy tells spacetime how to curve. Spacetime tells mass energy how to move. It is a dance. A feedback loop. A single equation, written in 1915, that predicts black holes, gravitational waves, the expanding universe, and the precise timing of your phone's map app. All from the idea that parallel lines need not stay parallel. Now, let's imagine a different universe. Suppose the cosmological constant lambda were much larger. Then dark energy would dominate earlier. Galaxies would never form. The universe would expand so fast that no two particles could ever meet, no stars, no planets, no us. Parallel geodesics would diverge exponentially from the start. Or suppose lambda were negative. Then the universe would recollapse, like a sphere in time. All geodesics would eventually meet in a big crunch. Parallel lines would converge everywhere, inevitably. Our universe sits near the knife edge, lambda small but positive, allowing structure to form, stars to burn, life to arise. Why? We don't know. It's the cosmological constant problem, one of the deepest mysteries. The predicted vacuum energy from quantum field theory is 10 to the 120 times larger than observed. Something cancels it, almost perfectly. Perhaps the geometry of extra dimensions. Perhaps a multiverse. Perhaps something we haven't imagined. But in this universe, in this epoch, parallel lines can meet if they're near mass, and cannot meet if they're in the void, pushed apart by dark energy. Both are true. Not contradiction. Complementarity. Like wave and particle. Like rest and motion. Like sleep and learning. And so, as the ideas settle, not like stone sinking, but like dust motes in still air, let us return, once more, to the beginning. To 2 lines. Not on paper. Not in a textbook. But in the quiet dark behind your eyelids. Imagine them again, drawn not with ink, but with intention. Side by side. Equal. Unmoving. At first. Now, let one pass near a star. Let the other drift through empty space. Watch. The first line bends, not because it chooses to, but because the space it moves through is shaped by mass. Its path is still straight as possible, but the meaning of straight has changed. The second line remains unbent, Euclidean, serene, because where it is, space-time is flat. Are they still parallel? At the start, yes. At the end, no. But neither has done anything wrong. Neither has broken a rule. The rules themselves have depth. They have texture. They respond. Geometry is not rigid. It is resilient. It is relational. It listens to matter and answers. You do this, too. Every time you stand, you press against Earth's curvature. Every time you look at the stars, you see light that has followed bent paths for thousands of years. Every time your phone pings a satellite, you join a global network that only works because engineers said, yes, time flows differently up there. Yes, space is curved. Yes, parallel lines meet, and also do not. And we will build our world on that truth. That is courage. Not the loud kind. The quiet kind, the kind that trusts observation over dogma, that revises its map when the territory reveals new contours. Euclid was not wrong. He was local. His geometry holds in your room, in your notebook, in the space between your hands. But step outside, step into orbit, into the cosmos, into the deep structure of reality, and the lines begin to breathe. They converge at poles. They diverge in voids. They oscillate in waves. They loop around black holes. They stretch and squeeze with the rhythm of colliding stars. They carry the history of the universe in their angles. And you are moving among them. Your world line is a geodesic through space-time, woven from stardust, shaped by gravity, illuminated by light that left the sun 8 minutes ago. You are not separate from this geometry. You are of it. Your bones know curvature, they grew under 1G, aligned with Earth's field. Your eyes know light, they trace null geodesics to your retina. Your mind knows patterns, it seeks straight lines, even when the world offers curves. And tonight, you are letting go of the need for flatness. Letting the tension in your shoulders ease, not because the world is simple, but because it is coherent. It makes sense, not in a single voice, but in a chorus. Newton's laws for bridges and baseballs. Einstein's for satellites and stars. Quantum rules for atoms and light. Each valid in its domain. Each part of a larger harmony. There is no contradiction in parallel lines meeting and not meeting. There is only scale. There is only context. There is only the shape of the question you ask. So as you drift deeper, past the numbers, past the names, past the history, feel the simplicity beneath. Space-time tells matter how to move. Matter tells space-time how to curve. And in between, us. Not passengers. Participants. Every heartbeat sends a ripple, tiny, yes, but real, through the gravitational field. Every thought is a pattern of charged particles, moving along geodesics in curved electromagnetic and space-time fields. You are not in the universe. You are the universe, observing itself. Learning itself. Resting itself. And in this rest, something remarkable happens. The mind, freed from urgency, begins to absorb, not by force, but by resonance. Like a tuning fork vibrating when the right note is sung. Like geodesics aligning when curvature is gentle. You don't need to remember the Riemann tensor. You only need to feel, in your bones, in your breath, that the world is not rigid. That it bends. that it connects. That what seems impossible, parallel lines meeting, is not magic. It is measurement. It is truth. It is the earth, round beneath your feet. It is the GPS, guiding you home. It is the light from a distant quasar, bent into a ring by a galaxy cluster, showing us the invisible. It is the quiet hum of space-time, vibrating with the memory of colliding black holes. All of it, real. All of it, here. Now. As you breathe in, space-time expands. As you breathe out, it contracts. Not metaphor. Not poetry. A reflection. A resonance. You are made of the same stuff that curves. And so your rest is not passive. It is alignment. It is trust. It is the deepest kind of knowing, the kind that does not shout, but settles. Like two particles, falling side by side, in the gravity well of a star, no force between them, yet moving as one. Like two lines, drawn on an orange, meeting at the pole, not because they turned, but because the world they live on is whole. You are whole. The universe is whole. And in that wholeness, there is room for meeting and for not meeting. For motion and for rest. For question and for answer. For waking and for sleep. So let go now. Let the formulas fade, not forgotten, but absorbed. Let the names, Gauss, Riemann, Einstein, become stars in the background, distant and steady. Let the satellites orbit. Let the light travel. Let the geodesics find their way. You do not need to hold it all. You only need to be here. In this moment. On this planet. In this quiet. Where parallel lines, somewhere, in the dark, do exactly what they need to do. And you are exactly where you need to be. Safe. Still. Falling, not down, but in. Into the curve of space-time. Into the rhythm of the cosmos. Into the deep, gentle truth. You belong. You always have. Good night.